This school will be an invitation to dynamics, complex dynamics, and in particular algebraic surfaces. So we will continue through the day. There will be breaks for coffee, lunch, and we will have 4 talks. For the first speaker today, we're extremely pleased to have our own Mikhail Lyubich, who will give us an introduction to dynamics on the complex projective line. If you want, we will steer depending on how you look at these things.
Okay, if you're a dynamicist, you call it the Riemann sphere. So if you're algebraic geometry, probably call it differently. So anyway, so yeah, thanks a lot for this invitation. I think that it's a great idea to try to make people in dynamics and algebraic geometry interact. So I believe that dynamics is a great source of problems for algebraic geometers who have all the tools in their possession to to address these problems. And actually, it seems that recently it also started to work the other way around, that dynamics provide some ideas which are useful to deal with some problems in algebraic geometry and number theory. So, well, my goal today will be just to introduce people here who have not heard anything basically about this subject into the basics of the holomorphic dynamics in dimension 1. So what we will be dealing with is, that is a fancy chalk. Okay, let me try how it works. So we are dealing with just a rational function in one variable. So we think of this function as the map from the Riemann sphere to itself. So that is a very simple object from the point of view of algebraic geometry. I guess nothing to ask about it, but if you're in dynamics, you think of this as just the first iterate of your dynamical system. So you start to consider further iterates, the f squared, it is the second iterate, etc., f to the n. It is the n-fold iterate of your map. So you iterate n times. And so today, f to the n will mean nth iterate, not the nth power, not as nth algebraic power, but just nth iterate of your map. And so you obtain some semi-group of endomorphisms of the Riemann sphere. You try to understand it from the dynamical point of view. So you take some point, z, and you try to understand what happens under iterates, so with this point. So z goes to f of z, goes to f squared of z, etc. So it is doing something. So what is it doing asymptotically? So what are the terms to describe it? And the next problem would be to understand how this depends on parameters. So very interesting, deep problem, but today I will not address this one. Today I will be talking just about iterates of one single map. So how to think about this dynamical system, this semi-group of transformations. Okay, so so this map has degree. I will usually denote it by d today. Degree, just algebraic. It is algebraic degree, which is the maximum of degree p and degree q. And it is also topological degree, so topological degree of this branch covering of the Riemann sphere into itself. And my standing assumption will be that degree is at least 2. In degree 1, we have a Möbius transformation, and dynamics of a Möbius transformation is very simple. I will not comment on it. You can do this as your exercise tonight. So what happens with one Möbius transformation? Okay, so it is a very classical topic. So the founders of this subject were Fatou and Julia in the beginning of 20th century. And so one first step they did is to decompose the Riemann sphere into 2 parts. And these 2 parts are now called the Fatou set and the Julia set. So, and this decomposition corresponds to some regular dynamics on the Fatou set and some chaotic dynamics on the Julia set. And this decomposition was related to the tool which was very new at that time in the beginning of 20th century, just appeared. It is Mantel Theorem theory of normal families. Mantel theory of normality. So what is normality? So let us assume that we have some family of meromorphic functions. So meromorphic functions, it is just holomorphic maps from some domain, some one-dimensional domains, the domain in C or on the Riemann sphere, into the Riemann sphere. And so this space of such functions can be endowed with compact open topology, so topology on uniform convergence on compact subsets on U. So compact open topology. And the normality means just precompactness in this topology. On the Riemann sphere is compact, so here you use just you use a spherical metric. So, and here you just use any metric because you restrict on the compact sets anyway. So normality is just another word by precompactness, but somehow in the holomorphic theory, in the complex theory, there is a special word, and maybe there are good reasons because there is a very different flavor for of this property. So namely, there are very, very good conditions for normality, and that was one of the Montel's discovery of early 20th century. Well, the simplest theorem of this kind, simplest Mantel theorem, is the following, that's something that everybody learned as undergraduate. So little Mantel theorem is that if we have a family of holomorphic functions, so U is some domain in the complex plane, and we have a family of functions to the unit disk, or to some disk for that matter, then it is normal. It's normal. So any family like that is normal, or the full family of such functions is normal. And there is a very simple reason, but very specific to holomorphic setting, is that the derivative of a map can be bounded by the bound of the, if the map is bounded, that you can bound derivative just on some smaller subset. And once you bound, you have a bound on the derivative, then you have equicontinuity, and then equicontinuity produces for you compactness. So it is, you see that it's very simple theorem, but it is very holomorphic because the derivative can be bounded by the function itself. So not for just in general continuous setting, but in some special setting like holomorphic. Somehow, what was remarkable is that this very simple result can be almost immediately promoted by very surprising and very strong result. It is a big Mantel theorem. Big Mantel theorem, which would tell you that if you have a family of functions on U to the Riemann sphere with 3 punctures, and well, it does not matter where to put these 3 punctures because there are freedom of applying Möbius transformations, so we can put these 3 punctures to 1, 0, and infinity. So I just remove hat from here. So if you have a family of holomorphic functions which emit 2 values, that such a family is normal. Such a family is normal. So
remind me just concretely what normal means.
So normal means that you have, well, it is precompactness in this topology, and well, formally speaking, it means that if you have any sequence of such functions, then you can select convergent subsequence. Convergent, there, for any sequence, for any Fn, there exists a subsequence f and k convergent to some psi uniformly on compact subsets of U. So that is formal definition of just compactness in this topology.
Sorry, if this was asked, can I ask how is that related to the derivative? You were mentioning the derivative for.
Yeah, I see. So, well, for the family of continuous functions, there is classical Ascoli theorem that tells us that precompactness in the family of continuous functions is equivalent to equicontinuity. So, equicontinuity of this family of functions. If the distance between 2 points is less than epsilon, as the distance between the images is less than delta.
Uniform
continuity, equicontinuity, uniform continuity. And if you have a bound on the derivative, then you have uniform Lipschitz constant, so you have a uniform continuity. Bound of the derivative obviously imply precompactness. And the Cauchy formula implies very easily that if your function is bounded on the unit disk, for instance, that the derivative will be bounded on any smaller disk. So there is a bound. It is very simple and extremely important and remarkable property of holomorphic functions, that you can bound derivative through the function itself using the Cauchy formula for the derivative. And it is the basis. It is the basis for all this development. So there are two ingredients here: this Cauchy formula, which gives us a small Mantel theorem, little Mantel theorem, and then there is a topological, basically, observation, which was also very new, I think, quite fresh those days, is that if you take the sphere with 3 punctures, and you can consider its universal covering, and then the universal covering will be the unit disk. So you have the unit disk D, which is the universal covering. It is famous function which does this universal covering. It is a modular function. So just you have triangular group. So there is covering with this, are associated with this tiling. So if you have a family of functions, say in the unit disk here, well, and the theory, normality is a local property. We always can think that the functions are defined. To prove anything, we can think that the functions are defined on some simply connected domain or in some small disk. So if you have family of functions like that, you can lift it to the family of functions to here, and you can derive normality of this family of functions from normality of that one. Or you can do even better. You can take the hyperbolic metric, Poincaré metric, on the unit disk and push it down to the sphere with 3 punctures, and you obtain a hyperbolic metric here, and then this family of functions will be contracting with respect from hyperbolic metric to here to hyperbolic metric to here, and this contraction will also give you uniform, so will give you equicontinuity, so it will give you normality. So there is this, but there is this very simple passage from this little theorem about bounded functions to this very big theorem about functions, Picard-like theorem about families of functions which omit 3 values on the Riemann sphere. And this was the foundation for classical holomorphic dynamics. And the definition of the Fatou set and Julia set is just based on the on this notion. So now we will consider a family. So we have our rational map, and we can consider a family of functions Fn from the Riemann sphere to itself. And let us say that a point Z belongs to the Fatou set if there exists a neighborhood of this point, or point Z naught belongs to the Fatou set. If there is a neighborhood of this point Z naught, U, such that the family of functions Fn restricted to U, to the Riemann sphere, is normal. Is normal family of functions. So that is just the definition. Or in other words, we take the biggest open set, so on the sphere, on which our family of iterates is a normal family of functions, normal family of meromorphic functions. That is the Fatou set, definition of the Fatou set. And by definition, the Julia set is just the complement of the Fatou set. So it is just definition. We have such a decomposition. And you see, so basically, immediately we see that Fatou set corresponds to some regular dynamics, and Julia set corresponds to some kind of chaotic unstable dynamics, because this regularity, stability is built into the notion of normality. So because it is normal, there is equicontinuity. If you take any point, some sufficiently close to z, and you start to iterate them forward, then they will stay epsilon distance apart. They will not go far away. So if these points were delta close, then all the images will be epsilon close. That is what is called Lyapunov stability. Lyapunov stability of the point z0, and it is equivalent to z0 belonging to the Fatou set. A point z0 belongs to the Fatou set if and only if it is Lyapunov stable. So all sufficiently closed points, all delta closed points have the properties that the whole orbit of this point stays close to the orbit of the original point. So there is this stability which sort of means that the dynamics is kind of tractable dynamics, not very difficult dynamics to understand, presumably. On the other hand, if we take a point on the Julia set, then normality fails in any neighborhood of this point. So, and if normality fails, then if we take the images of this iterate and take the union of these images, then it is the whole sphere except maybe 2 points, maybe. Just big Mantel theorem tells us that, so you take tiny neighborhood of the point on the Julia set, and it must spread all over the Riemann sphere. It can meet only 2 exceptional points. That's all. So there is a big instability immediately built into this definition. So on the Julia set, you have instability. On the Fatou set, you have stability. So by the definitions are designed so that it corresponds to regular and stochastic dynamics, regular and chaotic dynamics of the corresponding points. Okay, so now if we restrict ourselves to polynomials, so f of z is, and I will always normalize polynomials so that it will be monic, the leading coefficients will be 1. It can always be done of degree d. Then we can think. Then there is some special features for this polynomial, for this situation, which allow to give an equivalent but easier definitions of these sets. So in this case, there is a point at infinity which is an attracting point. So what happens for polynomials? So take the complement of the disk of big radius r, and then if you take a point z0 somewhere here, then its first iterate will be like z0 to the power d, so it will be much bigger, and then the next will be much bigger, and so fn to z0 will converge to infinity, and it will happen uniformly, of course, locally uniformly in this domain. So we see immediately that this domain is in the Fatou set, and actually it is in the basin of infinity. It consists of orbits which converge to infinity. So we can define the basin of infinity. Basin of infinity, by definition, is a set of points such that fn of z converges to infinity. It is some part of the Fatou set. So let us denote it d of infinity. D of infinity. So, and it turns out that if we consider the complement of d of infinity, it is usually denoted k of f. It is c minus d of infinity. Minus d, it is called field Julia set. Then the Julia set is just the boundary, the common boundary of the basin of infinity and this set. So the Julia set J of f is just the boundary of the field Julia set, and it is also the boundary of d of infinity. So it is a common boundary between the set of points that escape to infinity and the set of points that don't. So, and at this moment, maybe I should show at least one picture or a couple of pictures. So how the Julia sets, some standard Julia sets look like. Can I have the screen somehow? What should I press in order to? Oh, okay, thanks. So, should wait. Well, just one example of the Julia set. So it is just the Julia set of some quadratic polynomial. So just some polynomial z squared plus c. So, and
boundary of this object.
yes, so the basin of infinity is this blue region. So orbits here escape to infinity under iterates. So KFF, the field Julia set, is this dragon. So, and the skin of the dragon, this boundary, is the Julia set. So in the interior of the dragon, the orbits, well, in the whole dragon actually, the orbits by definition are uniformly bounded. So it is by little Mantel theorem, actually on the interior, the orbits, the set of iterates is normal. The family of iterates is normal because it's uniformly bounded. And here the family is normal because it is uniformly going to infinity. And on the boundary, in any neighborhood, some orbits escape to infinity and some orbits stay bounded. So there is instability. So the common boundary is the Julia set. So for polynomial case, it's always the case that we just should look at the basin of infinity, take its boundary, and it is our Julia set. So let me see whether I can get any other picture. Can I? Maybe not. I don't know what to press here to. Okay, so since that, then this would be enough for us. So just one dragon. So maybe Scott, you could help me to list it somehow, to scroll. Okay, so doesn't matter. So I will show you a more interesting picture. So, and I will not need the screen for that. Okay, there's some pictures of the same kind. So, and can we scroll down a little bit? No, further. Yes, there is a picture of different type when the Julia set and field Julia set coincide. So there is no interior in our set. That is the basin of infinity, and the complement of the basin is this dendrite. Dendrite is sort of like infinite tree. So, and it is our Julia set, and there is one more. It is also quadratic polynomials, and there is one more picture. And in this case, the difference is that the critical point itself, the zero, it's quadratic polynomial z squared plus c. So the origin plays a very special role for the quadratic polynomial. It is the critical point. It's right here in the center, and it's escape to infinity itself. And this fact breaks the Julia set into pieces. And in this case, it breaks into Cantor set. So just the Julia set here, and it is just the Cantor set. It's totally disconnected set. And everything outside of this Cantor set actually escapes to infinity. So that is another typical picture. And probably I will not need any more pictures on the screen. So thank you, Radu. So, but I will draw without screen some very much more interesting picture. Namely, I will consider c equal to 0. So our map f of z will be z squared. And then the picture of the Julia set will be that interesting. So it will be just the unit circle. So a sort of very rare situation when the Julia set is so simple. So, and the basin of infinity is just the complement of the unit disk. So here the orbits can escape to infinity. And inside of the unit disk, the orbits converge to the origin. It is another attracting fixed point in this case. And the Julia set is the unit circle, and it is very instructive to take a look what is happening on the unit circle. So it is just a map z squared on the unit circle, but let us write it in the angular coordinates. So angular, let me select angular from 0 to 1. So, so parameterized by rotations. So, so theta is r mod z. So, and then in the angular coordinate, the squaring is 2 theta, so mod 1. So it is what is called the Dublin map. The Dublin map in terms of the angular coordinate. And so to understand this Dublin map, it is good to use just dyadic decompositions for the angular. So let us represent as epsilon k over 2 to the k from 1 to infinity. So in epsilon k just from digit 0, 1, so dyadic decompositions. And so we associate to any point, we associate, well, it's not exactly one-to-one correspondence, but so it's better to write it this way, actually. So to any sequence of such digits, epsilon 0, epsilon 2, etc., infinite sequence of such digits, we associate an angular set. It is almost one-to-one. There is some ambiguity that we know from the high school, but it's not a big ambiguity. And the Dublin map, in terms of this decomposition, is a very simple map. It is what is called the shift, one-sided shift sigma, which is just forgetting of the first digit. So epsilon naught, epsilon 1, epsilon 2, etc., just transform to epsilon 1, epsilon 2, etc., because we double and then consider mod z. So we forget the first digit. So it is, in terms of dynamical systems, this is good to write in the following way. So we have this space of sequences. Sigma 2 is the space of one-sided sequences. So space of sequences like that, epsilon naught dyadic sequences, all dyadic sequences we consider, and we have this map to the unit circle T, and on the unit circle we have our Dublin map z squared, and here we have let me write it on this side, we have the shift map sigma, and we have this natural projection pi. So from this space of sequences to T, our coding, our just standard dyadic coding, and so we have such a diagram, which is called semi-conjugacy. So if this map was one-to-one, then it would be called conjugacy. Because it is slightly not one-to-one, it is called semi-conjugacy. So pi composed with sigma is the same. So sigma composed with pi is the same as pi composed with our map f, which is z squared. So when we have such a relation, then the dynamics upstairs becomes the dynamics downstairs. Orbits here are mapped to the orbits here, so basic dynamical properties can be transformed from upstairs to downstairs. And since the map is almost one-to-one, basically understanding of this Dublin map, it is almost the same as understanding this shift map. Okay, so for the Dublin map, we have an interesting measure. So on the circle, just the standard Lebesgue measure. So the standard length on the unit circle, and this length can be lifted to, so it is just Lebesgue measure, and it can be lifted, well, so Lebesgue, let me call it Lebesgue on the circle, can be lifted to some measure mu on this space of sequences. So what is this measure mu on the space of sequences? Well, so to understand this measure, we need to understand the measures of the cylinders. So the cylinder, so for instance, zero cylinder is a space of sequences which begin from 0 and then arbitrary, anything else. And 1, so there are two cylinders of this type, so cylinder like that, and cylinder 1, and it corresponds to partition of the circle into these two pieces, upper 1/2 and lower 1/2. And so the measure of each of these cylinders, epsilon 1, is equal to 1/2, of course. The length is 1/2. So we can consider longer cylinders 0, 0. It is the cylinder of all sequences that start with 0, 0 and then anything else, etc. We have four cylinders like that, and it corresponds to the partition of the circle into four equal pieces. So the length of each of pieces is 1/4. So the length of each cylinder of size 2 will be 1/4, etc. The further cylinders of length 3 will be 8 cylinders of length 3. Each of them will have a length 1/8, and in general, so the measure here of the cylinder E0, E1, E2, etc., En will be 1/2 to the n. Well, so that is something that everybody here recognizes, because if you start to toss coin, it is actually exactly the probability that this sequence of heads and tails will appear. So what we see here is that these sequences, typical sequences that appear here with respect to this measure, they just correspond to this random process of tossing of coins and of appearing of tails and heads, of tossing the coin. So here we have completely deterministic dynamical system. So everything, if you know a point, you know the whole orbit. But for all practical purposes, it is an absolutely random, chaotic dynamical system. Because if you watch the sequence and you just look how these digits appear, you code this trajectory, look how the digits appear. If you know with the first n digits, you can tell nothing about the next one. The next 0 appears with probability 1/2, and next one appears with the probability 1/2. And it is as random as you can get, because you know literal nothing from the past, you know literal nothing about the future. So no learning process at all. So that is already the simplest example. It is actually, in a way, the most chaotic example you can get at all. So just literally so. It is basically mathematical statements that I am making. So that this simplest deterministic dynamical system behaves like a sequence of independent random variables. Okay, so that is a very important lesson that we have to learn just looking at this system. Important properties that I would like to mention here of this measure. First of all, this measure is invariant measure. So the invariance so it could be a little bit strange at first glance, because it is a doubling map. So it looks like it increases the length of the intervals, but invariance should be understood properly in terms of the push forward. So you have a measure, then push forward of the measure is defined as a measure of the full preimage. Not the image, but as a full preimage. So that is a correct categorical definition of the push forward. And so it means X is some measurable for any measurable set. So if the measure is invariant, it is a property of invariance. If the measure is invariant, then it means that for any measurable X, the measure of full preimage of X is equal to the measure of X, which have to take full preimage. And if you take here, you take some interval of length epsilon, you take full preimage, it would consist of two intervals of length epsilon over 2. So the measure of the preimage will be the same. So the measure is invariant, and it's actually very obvious in the symbolic model that the measure is invariant. So, and also this measure has a very important, nice quality, which is called ergodicity. That is ergodic measure. Let me give you a definition. Ergodicity. So, and it means that there is no non-trivial decomposition of our phase space, which is the circle in this case, but the definition, of course, is general, X and Y, into invariant subsets, subsets. So it means that f of x is contained in x, f of y is contained in y. And non-trivial means that both the sets have positive measure. So non-trivial, that is the mean and non-trivial. There is no such, in this case, if your dynamics is indecomposable, then it is, well, so I guess algebraic geometry would use the term irreducible. So in dynamics, it's used the term ergodic. So the system is called ergodic. And a nice property of ergodic systems, which is the fundamental classical Birkhoff ergodic theorem, it tells us the following. So if you take some interval, some arbitrary interval here, and take a random point here, if you start to look, take the orbit of this point, if you start to look how frequently it visits this interval, then this frequency asymptotically will be proportional to the length of the interval. So it is classical ergodic theorem. So it is also this feature of, it gives us some sense of chaotic behavior. The orbits are so spread all over the place. So this ergodicity is actually much, much weaker property than this existence of such a sequence of independent random variables. Much, much weaker, but still it is some step towards understanding of chaotic behavior, ergodicity. Okay, that is as simple as it is. So that is the basic model, and not only for holomorphic dynamics, but one can say in general for dynamics, basic model of chaotic system. Okay, so now, let us go back to holomorphic. Let us go back to more general, our discussion of the Fatou and Julia set after we discussed the simple but very basic example of the map Z squared. And of course, you understand that in the very similar way, we can discuss the map Z to the D. Also, the Julia set will be the unit circle. All the difference would be that we would consider the space of sequences with D symbols rather than 2 symbols. That's all. So, and then all the rest is the same. Okay, so what can I say about this decomposition? Let us go back to our decomposition into the Fatou and Julia set. Let me summarize several properties, general properties of this set. So, well, first of all, of course, f of f is open by definition. So J of f is compact. Both of them are invariant. Both are invariant, and so and they're both invariant forward and backwards. You can take images and pre-images, and you will stay in this set. And also there is the following nice property that J of f is either nowhere dense. For instance, for the polynomials, we saw that the Julia set is always the boundary of the basin of infinity. It is always nowhere dense, or else. Or the Julia set is the whole Riemann sphere. This can happen only for actual rational functions. So, and it is also a quite simple exercise on application of Mantel theorem. So Mantel theorem easily implies this. I will not spend a couple of minutes. Could have spent a couple of minutes, but I will save them to show. No. Keeping this property, but I would like to give you an example, a very nice classical example, which should be appealing for this crowd. It is called Lattice example of the Julia set, which is the whole Riemann sphere. So it is based on the endomorphism of the torus. So let us consider torus T2. Let us think of this as Z mod is C mod Z. And let us consider an endomorphism of this torus, expanding endomorphism, which is just a Dublin map, which is induced by the Dublin map on C. So it induces some expanded endomorphism of to Z. So in this, no, it is just linear map. It is just.
But the lattice theorem too.
So it is just this. So we have lattice, some lattice. And it is fundamental domain for our torus. It is a complex plane. And on this complex plane, we consider the dilation. And this dilation descends to the torus.
Yeah, but Z squared.
Huh?
Z squared.
Z squared, sorry, yeah. Yes. Okay. Thanks. So modular the lattice. Okay. So and then we quotient the torus by the involution sigma, which is z goes to negative z. Yeah, so that you're saying that the dynamics should be nonlinear dynamics. This is great. No. Okay, so we quotient our torus by the involution, z goes to negative z, and we will obtain actually the Riemann sphere. So, and it will be the branch covering from the torus to the Riemann sphere, which is well known as the Weierstrass P function. So it's just elliptic function. So it sort of lifts to the elliptic function on the complex plane. Now, this dynamical system, it respects this, it commutes with this, well, it respects this involution. 2 points which are symmetric go to 2 points which are symmetric, so it descends to some endomorphism of the Riemann sphere. And so it means that this endomorphism satisfy the functional equation that pi of 2 of z, where pi is our Weierstrass P function, is equal to f of pi of z. It is a kind of Dublin formula for the P function. So this Dublin formula for the P function has a dynamical interpretation that it is semi-conjugacy between this endomorphism of the torus and some rational function on the Riemann sphere. And on the torus, just the usual Euclidean metric is expanded, so uniformly expanded by a factor of 2. And so it descends to some metric on the Riemann sphere, albeit with singularities, with consingularities, but it is okay. So still there is some singular metric on the Riemann sphere which is expanded by our rational map, and it's enough to ensure that the Julia set is actually the whole sphere. There is expansion almost everywhere. You cannot have this stability, stable behavior which happens on the Fatou set. So it is a very nice example which say people in number theory love. Okay, so let us continue. Now, let us try to understand the simplest possible behavior, the so-called periodic points, fixed points. And so what could be the simplest possible behavior of an orbit? Just if the point does not move at all. So if you take a point, z, and if f of z is equal to z, let me call it alpha. If f of alpha is equal to alpha, it is called a fixed point. Fixed point, and that's quite boring. So asymptotic behavior is quite clear here. But we can consider a little bit more complicated. So points which are called periodic points. So you take a point alpha, and it goes around and around, and it comes back under p-fold iterate. So there is a smallest p, of course, but also multiples of the smallest p are also called periods. So, and that is already more interesting behavior, and of course it becomes particularly interesting if we let p go to infinity, and we'll try to understand what is happening. So I can quote you statement by Poincaré, who said that periodic points is the only opening through which we can try to penetrate to the domain that was viewed inaccessible. So it is a kind of simplest behavior, but this simplest behavior gives us some opening into chaotic dynamics. And so how to understand periodic points? Well, there is a basic invariant associated to a periodic point, lambda, which is called multiplier. And it is just this multiplier is equal to the derivative of this p-fold iterate, where p here is the smallest period. The derivative at point alpha of the p-fold iterate. And this derivative should be calculated in any local chart. The answer will not depend on the choice of your local chart. And a lot depends on the properties of this multiplier, and the periodic points are roughly classified as attracting if the multiplier is less than 1 in epsilon value, repelling, so in this case, neutral in this case. And there is actually a further classification here. So there is a further classification of neutral points. So let me go here. So lambda is equal to e to the 2 pi I theta. So theta is the rotation number of our neutral point, and a lot depends on the arithmetic of this rotation number. If rotation number is equal to p over q, this point is called parabolic case. And otherwise, it is called irrational naturally, but the irrational case also branches into two parts, which are called, into two cases, which are called Siegel and Kramer. And in the Siegel case, the local dynamics near this point, let us think that it is just a fixed point. It is a fixed point of f to the p, but let me just, for simplicity, assume that it is f itself. And the map f can be conformally linearizable near this fixed point. So there could be some domain which can be mapped onto the disk such that the map reduces just to a pure rotation on this disk. It is linearizable case, and if this happens, it may or may not happen depending on the rotation number, and if this happens, then the case is called Siegel. And these points are in the Fatou set, obviously, and if they are not linearizable, then they're in the Julia set. And I should have said here also that it is easy to see that these attracting points are in the Fatou set, repelling points are in the Julia set, and parabolic points are in the Julia set. That is a sort of rough classification of the points according to the local properties. So of course, in attracting case, the points locally attract some neighborhood. So all nearby points locally converge to this cycle. In the repelling case, they are locally escaping. And in the neutral case, it depends. It is very subtle situation what happens in the neutral case. And the dynamics in the Fatou set is largely determined by the presence of by the nature of the periodic points that appear. And there is a full classification of the dynamics on the Fatou set basically in terms of the periodic points. And so now I will give you this classification. So classification of periodic Fatou components. Oh.
They exist, or at least one or something.
Periodic points?
Yeah.
Okay, so you would anticipate that there are infinitely many of them because periodic points are solutions of this algebraic equation. So it is algebraic equation. So f to the n is the function of degree d to the n. So it is algebraic equation of degree d to the n plus 1. So you anticipate that generically you will have that many periodic points. Of course, it could be some degeneracies, but it turns out that there could be only finitely many of them. So basically the periodic points grow at this rate, number of periodic points with period n. So there are plenty of them, but where they are located, these periodic points? It turns out that most of them are located on the Julia set, and very few are located on the Fatou set. But these few, they determine what is going on the Fatou set. Except, so actually, what is going on the Fatou set, to be more precise, determined by the attracting, parabolic, which are on the Julia set, but they determine what happens on the Fatou set, and Siegel points, obviously. So Siegel points. So these points that largely determine what happens on the Fatou set. And actually, okay, so now I will describe you what happens on the periodic components of the Fatou set. So what does it mean? You take a connected component of the Fatou set is an open set. It consists of at most countably many components, and typically you should think that it consists of countably many components. You saw this dragon with countably many components of the interior. So there are usually countably many components. Take one of these components and assume that this component is periodic. So it will be mapped onto itself. So what can happen for this return map onto this periodic component? And there could be the following scenario. The first, that there is an attracting periodic point here, and everything in this component converges to this attracting periodic point under the iterates of this return map. Very simple. Or it can happen that there is a parabolic point on the boundary of this component, parabolic periodic point on the boundary of this component, and everything in this component converges to this parabolic periodic point. Parabolic case, attracting case. Or it can happen that on this component inside there is a neutral Ziegel point where the map is linearizable, and it will be linearizable fully on this component, so the map looks like rotation, just a rational rotation. Up to conformal change of variable, the map will be irrational rotation on this component. These are called Ziegel disks. That's actually all that can happen for polynomials. For polynomials, nothing else can happen. For general rational functions, there is one more type of behavior. Well, it's not type of behavior, but type of components. It is like Ziegel components, but just instead of disk, you can have a topological annulus. And on this topological annulus, you can have irrational rotation. So it is called Riemann rings. Riemann rings. And that is all that can happen on periodic components. And it is basically classical theorem due to Fatou, Julia, Ziegel, Arnold, and Riemann. So this classification of periodic components, it is classical theorem. And then in early 80s, Dennis Sullivan came to the scene, and he proved that if you take any component of the Fatou set, then it will be eventually periodic. So eventually, one of these scenarios will happen. So due to this result, we have a very full and simple description of the dynamics on the Fatou set. So very simple description. So it is all that can happen on the Fatou set. You take component, it eventually becomes periodic, and on this periodic component, you can have one of these types of gears. So the story on the Fatou set is over. So it is a regular set, so we anticipated that it is easier to deal with it, and it turns out that it is actually remarkably full description is available for the dynamics on the Fatou set. So how to deal with the Julia set? So on the Julia set, the dynamics is chaotic, and so we anticipate some other ways of describing these dynamics. We would not anticipate this simple description, but rather some statistical description in the spirit of the description of the dynamics on the circle. But on the circle, we had a very simple measure, the Lyubich measure, and a very simple coding of the dynamics on the circle by binary sequences. So what happens in general with the Julia set, whether we have any measure which can replace the Lyubich measure on the circle, whether we have some coding, and so can we do such kind of descriptions. And actually, so a lot in this direction can be done. So it is, but now we have to go back to the ergodic theory and to try to understand dynamics of the Fatou set in terms on the Julia set, sorry, in ergodic terms. So what would be a natural way to construct an invariant measure? What could be a natural way of constructing an invariant measure? So let us go back to our symbolic description. So let us consider the space of symbolic space in d digits now, epsilon I from 1 to d, and the shift map on this space. And so what we can do? Well, we can, to construct a measure, we can do the following. So let us consider, well, let me start from 1 here, probably it's better. So let us consider some cylinder of length n. So we fix n digits and make the rest free. So we have 2 to the n cylinders. It is so finite set of cylinders. Let us put some measure on this set of cylinders. And for instance, we can just distribute this measure. For simplicity, we can distribute this measure. Well, it is if we construct Bernoulli measure. So if we construct Bernoulli measure, then we just distribute this measure uniformly on these cylinders. In general, it can be more general distributions, and we can go to next cylinders, etc. If there is certain natural compatibility properties, then we can pass to a limit and construct a measure. And of course, we need to be careful to construct invariant measure, etc. But that is natural way of doing that. But now a little twist for that. So let us now do the following. Let us fix some sequence, say delta 1, delta 2, etc. And let us start to take pre-images of this sequence. So it has two first-order pre-images. One of them in one cylinder, another one is in the other cylinder. On the next pre-images, and let us put on these pre-images, let us put equal masses. Let us take pre-images of order 2, then we should add arbitrarily two symbols here. So we obtain 4 pre-images, each one in each cylinder of order 2, etc. So if we consider n-fold pre-images, then we just write down here arbitrary sequence of n symbols, and each of these symbols sit in the corresponding cylinder. So if we distribute measure in certain way over these pre-images, then it is basically the same as distributing measure in certain way over the cylinders. So instead of distributing the measure over the cylinders, we can distribute the measure over the pre-images with the same result in this symbolic context. So what is the point of doing that? The point is that it is more general construction, because pre-images we can consider always. So we can consider, say now let's consider our rational map of the Riemann sphere, and let us take any point z, and let us take its pre-images, f to the full pre-images. It is generically d to the n points. Well, it is always d to the n points counted with multiplicities, but geometrically it could be a little less. So let us now distribute uniformly the measure, discrete measure, so finitely many points. Let us put the mass 1 over d to the n to each of these points. So let us consider the measure mu n, which is 1 over d to the n, sum of delta zeta, where zeta belongs f minus first of z. I should have put here f mu n z. So if there are multiplicities, then we can count with multiplicities. So okay, so that is our measure. And so we just, over the premise, so we are following this scenario. We distribute uniformly points over pre-images. And we hope that this can converge to something nice. And indeed it does. Indeed it does. And namely, so there is such a theorem. So for polynomials, it was proved by Brolin in '65. Brolin was a student of Carlisson, and it was his thesis. Here it is the only work he wrote, so he wrote this thesis. It was mostly survey of Fatou and Julia. And at that time, in between 20s and 80s, there were very few works in this field, very few papers. And this is one of these. So it mostly survey, but it contained a very important result. So it is for polynomial case. And so like 15 years later, I generalized it to general rational case, also in my thesis. So apparently it was a good thesis topic. So and the theorem is that for all z except at most 2, except maybe 2, and these exceptions, of course, are related to the Mantel theorem. So mu n z converges to the measure mu. So this measure mu is independent on z. So it goes to infinity. Independent on z. It is supported on the Julia set. Support of mu is the Julia set. And it is invariant. It is invariant. Ergodic. It gives also distributions of periodic points. Gives asymptotic distribution of repelling periodic points. Repelling periodic points. So repelling periodic points sit on the Julia set, and if we do this with these points, the same thing, we just take points with period n, equidistribute the uniform mass over this period and pass to a limit, then we get the same limit mu. And it also has the following nice interpretations. So it is a harmonic measure, on the Julia set. So that was interpretation by Brolin, and I'll tell you in a moment so roughly what it means. And it is a measure of maximal entropy, the unique measure, measure of maximal entropy. It is my interpretation. So, okay, that is a theorem which gives us natural measure, which gives some insight into the chaotic dynamics on the Julia set. Okay, so what all these words mean and how to approach the theorem. So I will try to, in the time which is left for me, I will try to sort of outline roughly so what are both. So the approaches were very different, and so I'll try to outline both of them, roughly speaking. So for Brolin, this measure was the harmonic measure on the Julia set, and so roughly what it means is the following. So you think of the Julia set, here is the Julia set, you think of it as a conductor, conducting, so piece of metal. So you put a unit charge, mu, on this piece of metal, and you let this charge to get into equilibrium. So it is equidistributed, so it will organize itself into some equilibrium distribution of the unit charge with the smallest possible potential. This equilibrium distribution is what is called harmonic measure. This distribution has a potential, G. G is the potential of this distribution. And this potential is a subharmonic function. The support of mu, by the way, will be also, we know from physics that support of mu should be the boundary of our set. So you can start with the field Julia set, for instance. Well, it is for the polynomial. So this method, I'm describing this method, Brolin method, it is f of z is our polynomial, z equals z, etc. So we can start with the field Julia set, but it will be supported on the boundary because the charge is never supported inside of the body. So it is subharmonic function which is harmonic outside the Julia set, which is the support of our measure, with the log behavior at infinity, and which is related to the potential in the following way, that the Laplacian of this function, of this potential function g, so is, well, up to this constant, it is our distribution, equidistribution of the charge. Charge and potential are related with, in this way. It is, of course, very well known for everybody in the case of a smooth distribution. When you have a smooth distribution of the charge, it is very well known relation. But in general, this should be, here we have a singular distribution of the charge, some singular measure with respect to the Lebesgue measure, and this relation should be understood in the sense of distributions. So that is kind of the definition of the harmonic measure. It is just equilibrium distribution of the charge, physical definition, equilibrium distribution of the charge on the Julia set. But what is remarkable, it was a remarkable discovery in the Brolin thesis, is that this potential has an explicit dynamical meaning. Explicit dynamical formula can be given to the potential, and the formula is the following. So if you take, let us take a point z, which is outside of in the basin of infinity. So in the basin of infinity, the map near infinity, our map z to the d plus blah, 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 it behaves like z to the d, so near infinity. If we start to iterate fn of z, it will be like z to the d to the n, or better I will put here not z, so let us take an absolute value, and then we can put here some r, and this r will depend on z. And how this r depends on z actually will produce for us our green function, namely the green function can be defined as a logarithm of this r in the basin of infinity, or it can be defined in this explicit relation. So this I just will decipher the meaning of this expression. It is limit 1 over d to the n logarithm fn of z. So we take a point z in the basin of infinity, it escapes to infinity in this rate, and somehow the escape rate is controlled by the green function by means of this explicit formula. Well, it is fairly straightforward to prove that this limit exists, that it's a harmonic function in the basin of infinity, and if we extend it by g equal to 0 on the field Julia set, it is just definition, then it will be a continuous subharmonic function on the whole complex plane. And it will have also other properties of the potential. So it will be harmonic there, so we'll have logarithmic singularities at infinity. And you see that it is equal, it is the field Julia set is the equipotential set for this function. So it looks exactly like a potential for some charge distribution. So let us define mu now. Let us define our measure as just generalized Laplacian, or 2 pi this measure, as a generalized Laplacian of this function. It will be a definition, and this everything will exactly fit. So, and that was a really remarkable discovery, that there is such explicit expression for the green function in the complement of the field Julia set. You see, you would not anticipate this kind of thing. It's a fractal set. So to find the green function in the complement of the fractal set is the problem of the type to find explicit uniformization of this basin of infinity. So how you would anticipate that domain with such a complicated boundary can be explicitly uniformized? And it turns out that it can be just in this dynamical way. The set is complicated, but it is easier somehow, miraculously, it is easier to uniformize it. And also there is this wonderful relation for the functional equation for the green function, which is obvious from this expression, that under the dynamics, the green function is just multiplied by d. So that is the functional equation, or it can be written also f star of g is equal to g, and it can be written as f star of mesh. So by taking Laplacian, we can write it as f upper star of mu is equal to mu. It is pullback, and this pullback basically means that, so we have a map f, it is a covering map, and so we take pre-images, fibers of this map, we distribute equally the masses on these pre-images, just put so equidistributed masses on these fibers and integrate over this measure. That is what is pullback of the measure. It is not very standard notion. Yes, by d. So d times mu. Yeah, thanks. Yeah. Mu. So the pullback of this measure has this nice property, and it corresponds to the fact that we equidistributed the masses on the pre-images. All right, so that was Brolin's approach, and somehow it is not difficult from here, well, to see, but I will not, say on this, because I would like to say a few words about my approach to the problem, so of this equidistribution of the pre-images. But from this approach, you can derive fairly easily from the modern point of view, at least, that the pre-images of the points go towards this equilibrium. So, but it looked, so when I looked at this Brolin's result, it looked like it is very special for the polynomial case because it uses the basin of infinity very substantially. And so I wondered what would happen in the general rational case. And so let me just say a few words of my approach to the problem. So, so what I considered is the following operator acting in the space of continuous function. It is an averaging operator over the pre-images. So I phi of z is equal to average over the pre-images zeta I f minus first of z. So just I take some continuous function and I average this function over the pre-images of the point z, and it is my operator acting in the space of continuous function. And if to look at this equidistribution property, it is basically equivalent to saying that the iterates of this operator converge to the integral over some measure mu. So that is that because this, when we start to iterate, it will be averages over the further pre-images, averages over the further pre-images. And the basic property for me, the basic property that should be established in order to prove this kind of results, so is so-called almost periodicity, almost periodicity of A. So instead of proving that this sequence of operators converge to this one-dimensional projector, we can first try to prove that this sequence of operators, that this sequence of functions is at least precompact, equicontinuous in the space of continuous functions. So operator is called almost periodic if for any continuous function, so its orbit is precompact. It was the basic property, and then there is a very well developed theory of almost periodic operators that allow to pass from this precompactness to actual convergence under certain circumstances that can be checked in this case. All right, so and let me just tell you what is the basis for this precompactness. So we have to check some equicontinuity. I have like 5 more minutes or less, more. Okay, so let me then not to tell you how to check precompactness. So it was just this my approach, and it is related. So somehow we need to check the equicontinuities for the pre-images, and it is also related to normality of the family of inverse branches of our map. So let me restrict myself to this because I wanted to say just a few words of what is this entropy interpretation. So what entropy is, and I think that I may need 5 minutes for that. Okay. Okay, so what is this entropy? The entropy. So again, it is the best to understand entropy. Well, first of all, everything is based on the Shannon inside. Then if you have some event with probability p, then information contained in this event is equal to negative log p. It was Shannon inside, which is a little bit counterintuitive. So the less probability, the bigger information. So there is a famous explanation for that. So if you pick up a telephone, and so if you hear hello, then it is 0 information, of course. But if you are struck by the electric shock, then it's a huge amount of information that you have received. So that is kind of explains that this formula is indeed meaningful. So now if you have a sort of probability distribution, n events, or d events, p1, pd, you want to consider the average amount of information over this. It is, so let us call this probability vector p. H of p is negative, is this sum pi log pi. So you average information over this probability distribution. And there is a wonderful exercise. Everybody in calculus class should do this exercise, that if you maximize maximize h of p over the all probability distribution, then it will be equal, the maximum will be exactly log d, and the only maximal point will be the equidistribution. So for p equal 1 over d, etc.
T is the sum of the log.
The sum, yes. I use instant conventions.
Okay. Sorry.
So there is only one in the here. Okay, so you average over the whole thing, and so that is the key for understanding of entropy. So now it was Kolmogorov's insight how to define entropy for the symbolic sequences, for the symbolic systems. You just take the space, our space of sequences, sigma d. So then you can consider partition, you can consider the cylinders of length n. So, and you consider the probabilities. So you have some invariant measure on this space of sequences. And you consider these probabilities. There are d to the n cylinders here. And you consider the probability distribution for these d to the n cylinders. So it is finite probability distribution. You calculate Hn is the average information contained in this probability distribution, this average information contained in this probability, and divide by n, and it converges to the entropy of this sigma with respect to this invariant measure. So that was an important invariant. So it was a new invariant in early 50s, which allowed to distinguish certain dynamical systems, measure theoretically distinguish certain dynamical systems. And so there is a fairly, not very difficult, but non-trivial theorem that there is a unique measure of maximal entropy. The unique measure, and of course, to get a measure of maximal entropy, you need to try to equidistribute these guys in an equal way. So it is our friend, this Bernoulli measure corresponding to independent random variables. So for this, it is fairly simple theorem. So, but now if you have a more general system f with measure mu, what you can do, you can partition, like for the circle. For the circle, we have some partition of this measure of the space into two parts, upper half circle and lower half circle, and it produced for us some coding of our system. Now you can partition into pieces. So piece x1, x2, etc., xd, and then you take any orbit, and then you can code this orbit according to how it visits these pieces. So you can consider to each partition you can associate some coding of the system. So it will be some semi-conjugacy between your original system and the symbolic system. So you can calculate entropy for the symbolic system, and then you just take supremum over all these partitions. I think that was Sinai's step to take this supremum over all these partitions, to pass from arbitrary symbolic to this system. And it is entropy, general entropy distribution, and you see that more equally you distribute, so that if you distribute equally, you anticipate that it will maximize the entropy. And here's exactly what we are doing. We take these pre-images and distribute the mass and pass to the limit. So you anticipate that you would get a unique measure of maximal entropy, and that's what actually happens. And so let me stop here. Thank you. Thank you.
Questions for Lisa? I mean, so I had a question. I mean, so degree one case, it's easy. What I mean, is there a difference between degree 2 and higher, or I don't know, or
so
really
so in the discussion that we had here, there is no difference. But if you go to some deeper questions, then the difference emerges. For instance, the quadratic family, z squared plus c, it has some special features. For instance, the parameter space is one-dimensional, z squared plus c. There is one parameter. And if you're interested in parameter space, you immediately have some special features coming, special advantages coming from one-dimensional modular space. So, and if you go to rational functions compared with polynomials, also there is some differences. So it becomes, yeah, deeper theory is degree sensitive. Degree sensitive and is sensitive to whether you consider polynomials or rational functions. But this discussion. Yeah, one thing that I maybe want to say is that in this level, somehow Brolin's and my approaches look very different. So rational functions look very different from polynomials. And it turns out that these theories can merge, but in high dimensions. It's probably what would be a sort of simple consequences of the further lectures today. So that kind of there is the unification of these two situations.
Any further questions? Always not. Let's thank Misha again.